Okay, so we talked about power in class already, but I just want to go over a couple things and add one thing that's new. So last year in conceptual physics, we basically said that power equaled work divided by time. What I didn't really tell you though at the time was that's average power. Okay, so that's like for a long process, I do the total amount of work that was done divided by the total amount of time it took, and that would give me the average power. That does not give me the power at any given moment. If I want to get the power at a given moment, that's instantaneous power. How about this one? And that is that is the rate of change of work, basically. Okay, the instantaneous time rate of doing work. I like to call it the rate of change of work, though. Okay, now there's a little weird math thing we can do here. If we keep in mind that work equals force times distance times the cosine of the angle between those two things, then if I were to take little pieces of that, so work is like force times the whole distance you push it or pull it or whatever times the cosine angle between them. What if I just do little pieces? So instead of pushing it a giant distance here, I just push it a little tiny piece of a distance. We call dx. It's a little tiny little slice. Okay, then I get this tiny little slice of work. Okay, so it's kind of like instead of pushing it, say if I had a box and I push it at some force at some angle and it goes a whole distance x, I'm not going to push it the whole way. I just want to go a little slice. If I just push it this little tiny slice here, then the total work is fx cosine theta, but the work done just in this little tiny slice, we're going to call it a little slice of work, and that's f little slice cosine theta. I'm sorry. I'm hungry. I shouldn't be doing this when I'm hungry. I get delirious. Okay. Well, that means I can come over here. Wait, I'm pointing the wrong thing. Hang on. Okay, I can come over here. I can say, hey, wait, power. Well, dw, I just said, was this. So I'm going to replace the top here with f dx cosine theta. I still have dt on the bottom, though. Okay. Wait a minute. Look at this. Actually, let's do a little... Oh, come on. Okay. See this bit right here? This stuff? dx over dt. That looks familiar to me. In fact... Oh, come on. What am I doing? I'll use green. Okay. In fact... No, I won't. Hang on. Okay. Wow. I shouldn't do this when I'm hungry. Okay. I'm going to take this stuff here and kind of shift it over to the right. So I've got this stuff left over. Okay. dx over dt, that's velocity. Remember the rate of change of position? That's velocity. So I can replace all of this with a v. Okay? So what I really have here is that the instantaneous power, the power at any given moment, is equal to the force you're pushing with times the velocity of the thing at the time times the cosine of the angle between the velocity vector and the force vector. So I'm gonna rewrite this a little bit nicer. Okay. Instantaneous power is equal to the force you're pushing with times the velocity the thing is moving times the cosine of the angle between the force vector and, say this thing is moving that way, the velocity vector. This would be my angle. Okay. This can be really, really useful. We're going to have some problems with this in class, but make sure you write that down. It's really cool. Another way to write this is in dot product notation. So the power equals the force vector dot the velocity vector, dot product. All right.